Any questions about anything before we start? Alex?
How heavy do you estimate these boards are?
Oh, holy moly, I don't know. The question was, how heavy do you think the boards are? Any other questions? Oh, all right, Will first. Oh, you didn't see it live. Well, at the end of the day, video not is as good as live, etc., etc., etc.
So, Alex is wondering if you could ride up the board to get the key in the ceiling.
Oh, yeah, there's a key stuck into the ceiling. We don't know what that unlocks.
No, all I know is how heavy the boards are.
Honestly, I don't know. Well, you could maybe. No, does any of you know Trisha Day?
Yeah.
Okay, we used to joke with her every class, like, "Hey, Trisha, could you go down in there and get the chalk?" Or, "Hey, Trisha, could you do this?" She liked that. No, she totally liked that. Any other questions? Yes. Wait. What? Any chance of what? Oh, Victor. The fans don't want to look at the back of your head, I guess. Does that help? Well, why hasn't this been a problem before? Why hasn't this been? Yeah, exactly. Okay, any other questions? Yep.
Is there a lecture on Tuesday?
There is a lecture on Tuesday. Yes, absolutely. Nothing on Wednesday, though, because that's no classes that day. Yep. Next week? You got to be kidding. Is this just a postponed class? Is this? Anything else? Exam, what about it? Recall, prelim 2. What do you want me to do? It's not done yet, no. No, it's sitting on my dining room table. Sitting on my dining room table.
Don't grade it until like after taste.
Yeah, I'll try to get around to it this weekend, but I don't know if it's going to happen. We'll see. We'll see.
With yesterday's lecture, should we like try to?
Oh yeah, okay. So let me just. We finished the FFT, and really there was only a bit of that lecture that was polluted by the bad diagram. It was only like 2 boards worth. And if you look, I sent out that email, there are diagrams for the FFT on Blackboard, and there's one figure 4 in that handout that says graphs for the DFT and the FFT or whatever. That's the one I was trying to draw. And everything I said about the little butterflies was right. And I think part of the reason I was having such trouble getting the coefficients on the branches of the little butterfly was that my picture was wrong. You know, I thought, wait, no, it's not this, it's not that. And so I apologize for the wrong picture, but the right picture is in the Blackboard handout, and everything else we said was true. Did that answer your question? Or yeah, I wasn't sure where you were going to go with that. But.
Yeah, I just wanted to know like what part of it specifically made it affect sort of.
Well, everything, as I recall, the picture up there, and then this board, and then I drew this kind of wavy line, like everything up to that wavy line. I don't know if you wrote the wavy line down.
Oh, I made a bracket.
Ah, okay. Anything else? All right. So now we're going to talk about the Z-transform. And this is something we touched on in 2200 last spring, but really we were only talking about what's called the unilateral Z-transform. We were using it as a tool to solve difference equations, essentially. And what I want to do is I want to give you sort of the whole story on the Z-transform. It's not very hard, but it's something you should know. And I think depending on who you took 2200 from, you might have gotten more of the Z-transform or less of the Z-transform. Like, how many people took it from Tong? How many people took it from Dorshuk? Okay, how much Z-transform did you do? A decent amount. Yeah, and he emphasized the concept of region of convergence, which is something we de-emphasized last spring because it's kind of trivial when you're just talking about the one-sided version of it. But that's going to play an important role in what we talk about here. And as he says to me, I don't like it when they give me a Z-transform without region of convergence. No. Can you hear him saying that? The Fourier transform. It's not quite as good as the Martinez. But. Okay, so anyway, what's going on? We're going to need to look at power series. And again, I'm just going to assume, for ease of exposition, that all the signals we talk about are going to be complex values. Valued. So power series of the form sum from n equals minus infinity to infinity, x of n, z to the minus n. And here, x is some discrete time signal, complex value discrete time signal. And the little z paired in that series is a complex variable. So it's allowed to range over the complex numbers or some subset thereof. And obviously, maybe not obviously, but for most x's, for most signals x, there's going to be some z values that make that infinite series converge. There's going to be other values of z that don't make that series converge. And that's the kind of thing we're going to have to understand when we deal with Z-transforms. Okay? So note, for that series to converge, both of these series must converge. And one of them is going to be the right-hand side of the series, the sum from n equals 0 to infinity of x of n, z to the minus n. And the other one is going to be the left side of the infinite series, the sum from minus infinity to minus 1 of x of n, z to the minus n. And why is that true? Well, when we talked about infinite series, remember, when we had a doubly infinite series, we defined convergence of that series to be convergence both of the right side of the series and the left side of the series. Okay, so for that series to converge, we need both of those to converge. So what I want to do is I want to look at those series. The right side and the left side. And ask the following question. So the big question is, given x, does that series converge, which is the same thing as do both of those series converge? And for some x's, there's going to be no values of z. So caution, for some signals x, no values of z make the series converge. And those are the signals for which we're not going to have Z-transforms. But suppose that you have a signal, a fixed value of z for which, say, the left series converges or the right series converge. Okay, so let's consider the quote-unquote n bigger than or equal to 0 series. Notice it takes a special form. It's a power series at z, and that's what makes the analysis of these things easy, or relatively easy. So suppose it converges when z equals, say, z0. So z0 is some number that you can plug into that right-hand series and get it to converge. The claim is that if it converges for z0, then it converges for every z value whose magnitude is bigger than the magnitude of z0. So in this case, the series also converges for all z satisfying the magnitude of z bigger than the magnitude of z0. Now, why is that the case? Well, here's the basic idea. The proof is in the monograph. So say you have such a z, and you try to plug it into that right-hand series. Sum from n equals 0 to infinity, x of n, z to the minus n. And now I'm going to do this little trick here. It's the sum from n equals 0 to infinity of x of n, z0 to the n, times z over z0, or z0 to the minus n, to the minus n. So all I did was I put a z0 under the z and a z0 to the minus n outside to cancel that operation. Because the series converges at z0, so because it converges at z0, the terms x of n z0 to the minus n in magnitude are less than or equal to some m, some finite m. Otherwise, you couldn't possibly have the sum of all those things, x of n z0 to minus n, converge. So this thing is going to be less than or equal to m times the sum from 0 to infinity of z over z0 to the minus n. And why does this converge? Why does that series converge? Remember, magnitude of z is bigger than the magnitude of z0. What kind of a series is it? It's a geometric series. So this is the same as m times the sum from 0 to infinity of gamma to the minus n, where gamma is equal to z over z0. And we know that this is going to converge when gamma is bigger than 1. Notice because we have a negative in the exponent. And therefore, it converges. So this converges because the magnitude of gamma is bigger than 1. So the bottom line here is that if the right-hand series converges for some z0, it converges for every z0 bigger than that in magnitude. Same argument applied to the left series. Yeah. Well, gamma is bigger than 1, but gamma to the minus n is the nth term in the series. And so having gamma be bigger than 1 in magnitude is what makes the geometric.
Oh, right.
Yeah. I could have made gamma be z over z0, but I, didn't do that today. So, or z0 over z, and had that raised to the n, but I didn't do that. Okay, so a similar argument shows that the left series, and I'm going to refer to these two series as the right series and the left series quite a bit. The left series satisfies the following. If the left series converges for z equals z0, then it converges for all z satisfying magnitude of z less than magnitude of z0. Same exact argument works, just playing around with infinite sums, geometric series, blah, blah, blah. Okay, so having noted those two facts about the right series and the left series, we're ready to define the Z-transform and region of convergence for a signal x. Okay. So given these observations, we define the Z-transform as follows. Okay. X in C to the Z is said to be Z-transformable when the following conditions hold. First off, the series sum from n equals minus infinity to infinity, x of n, z0 to the minus n converges for some z0. That's the first thing you need. And the fact that that converges for some z0 means that both the left series and the right series converge for that z0. Second thing you need is if you set R sub A to be the nth of all the magnitudes of z values for which the right series converges, and R sub B be the sup of all the magnitudes of z values for which the left series converges, we require, and by the way, well, I'll mention that after I say this. We require that RA be less than R sub B. And by the way, this seems very technical, I think, probably to most of you, and I'm pretty sure I'll be able to unwrap that in a satisfactory way after stating the formal definition. So we need R sub A less than R sub B. And if these two things hold, if the whole series converges for some z0, and if R sub A and R sub B, which are well defined, and by the way, R sub B, by convention, R sub B equals infinity is possible. What that means is that the left series converges for all z. And we'll see examples of that in a second. If these two conditions hold, so when these two conditions hold, you define the Z-transform of X as the following. It's going to be a two-part definition. It's going to be a function x of z given by the series x of n z to the minus n summed over all n. And this is what we call the formula part of the definition. And a stipulation r sub a less than magnitude of z less than r sub b. And this is what we call the region of convergence, which I abbreviate frequently as ROC, or maybe, depending on the context, ROC sub cap x. That's the definition of the Z-transform. First, we define what it means for a signal to be Z-transformable, and then under those circumstances, we define the Z-transform to be this. The point is, by our observations about the two series, the left and the right series, if you define R sub A and R sub B the way we did, here's the idea. The right series converges for all z satisfying Z bigger than R sub A. The left series converges for all Z satisfying Z less than R sub B. And therefore, the whole series converges for all the Z's satisfying both of those conditions. So that means that the whole series converges for all Z satisfying both of those conditions, which are the ones whose magnitudes lie between R sub A and R sub B, strictly. Comment. Sometimes but not always, the series will converge for one or more Z values that are right at R sub A or right at R sub B in magnitude. So sometimes the series for X of Z converges, and we're going to see examples of this in a moment, for one or more Z values that are on the boundary of the ROC. That is to say, magnitude of Z equals R sub A, or, and this is an XOR, magnitude of Z equals R sub B. They can't equal both because R sub A is less than R sub B, but we never include magnitude Z equals R sub A numbers or magnitude Z equals R sub B numbers in the ROC. So, but by convention, the ROC doesn't include these. Okay, now, there's the definition of R sub A here and R sub B is a big abstract thing. It's an inf of a big set of Z values, magnitudes, or soup of a big set of Z values, magnitudes. You may say, oh my God, how am I ever going to find an ROC in this lifetime? As it happens, all the interesting examples we look at, the ROC just pops out from geometric series type reasoning. So I want to kind of give you a little reassurance and hope that the ensuing examples confirm it, that finding R sub A and R sub B, equivalently the ROC for these things, is not going to be a lot of work for you. So, turns out, in most examples of interest, the R sub A and the R sub B, hence ROCX, just sort of quote-unquote pop out of simple geometric series reasoning. Okay, so let's go through these at Q-sub. What is, say that, written down, and. Let me put that. Does that look more like an and? Yeah. I guess I should put this, right? No? See, whenever I see this, I think of the LaTeX, delimiter operator, in an equation array, and equals and. You guys are pretty good at that, by the way, the ones who've been using it on Piazza. I must compliment you. You know what? One of my colleagues, who I really like a lot in the OR department, we were just up by the TV that tells, what's happening in ECE. And the ad went up for HKN giving a session teaching LaTeX, right? Which I think is great. He said, what is HKN? I told him what it is. And then I mentioned Piazza. And I said, well, in Piazza that you could do LaTeX and the students are pretty good at it. And he said, yeah, I don't use Piazza. And he said it was too much like being a helicopter parent. Do you think that's true? See, to me, it's a huge time saver because half the time you post a question and some other student or Joel or whoever answers it. And I could check the answer, and if it's right, I don't say anything. If I want to add something, I add something, right? So that saves me having appointment after appointment to answer a 2-minute question. Now, do you find it convenient as well? Do you feel like your hand is being held? You don't feel infantilized? You don't feel infantilized by the system? That's a new... No, it's Sid Resnick. He teaches advanced, you probably never... He's taught 2700 a few times. Have you had Callister before?
Yeah.
In entrepreneurship or something? Oh, yeah, he teaches those kind of classes. I can't imagine teaching something like that. See, he must have an infinite patience, to teach that kind of
So
stuff.
he has a lot of, like, his Piazza is pretty...
Very dry.
Like, he gets really, like, a lot of people ask him questions about Piazza, and he, like, makes, like, lots of sneaky answers.
They're very short. Like, obviously, this from this lecture, so.
So is that a deterrent for questions? Is that intentional deterrent?
Asking stupid questions. Really bad.
No, but do you know what his motive for that is? Is it to try to make people study harder or not ask stupid questions? Or?
I think it's more because, like, very few people come. It's like a 180-person class, and I don't think people show up.
Is it on video?
No.
A lot of stuff
A lot of people don't.
What time's the clock?
It's 10:10 on Tuesdays, Thursdays.
That's not. 10:10 isn't out of range. 8:40, yeah. Yeah, that's.
It definitely is.
Yeah. All right, so let's just do some examples. Let's do some examples. So, some examples. And these examples are going to feather out into a big list of what I call prototypes that we use all the time. So here's some examples. First of all, signal x equals delta. That's obviously the first one to do other than 0, right? What do you think the Z-transform of that signal is? And what do you think the ROC is? Based on this complicated definition. Yeah, it's the constant function 1. And what is the ROC going to be? All of z except 0, because by convention we never include r sub a. Okay, so let's just plug in. Just try to plug into the series. And this is what I mean by the ROC just pops out using simple geometric series reasoning. We try to plug the signal into the series. X of z equals the sum from n equals minus infinity to infinity, x of n, z to the minus n, and see what happens. Play around with it. So if I plug in delta, the only non-zero term in that series is going to be the term at n equals 0, and that's going to be a 1 times z to the minus 0, and that's equal to 1 for all z. So what do we say to ourselves? We say this silently, unless we want our friends to think we're nuts. Saying it out loud is like reading while moving your lips. It's the best analogy I can think of. We say, the big series converges for all z. Therefore, the right series converges for all z. And therefore, the inf of all the magnitudes of z's for which the right series converges is 0, so r sub a is 0. And we say the left series converges for all z, which means the sup of all the values of magnitudes of z for which the series converges is infinity. Therefore, r sub b is equal to infinity. So the conclusion is that x equals delta And this is notation that I haven't introduced yet, but that's obviously a takeoff on Fourier and DTFT and all that. Goes with the function x of z equals 1, and the ROC 0 less than magnitude of z less infinity. This is R sub A, and this is R sub B. So this is ROC x, and this is the formula part. Okay, simple, very simple example. Next example. So, given some complex number, z0, doesn't have to be non-zero. Consider the signal x with specification x of n equals z0 to the n u of n for all n. Now, notice that if z0 has magnitude bigger than 1, this signal grows in magnitude as n goes to infinity. So it certainly is not going to have a DTFT. So if we want to do transform-y kind of things with this signal, we're going to need a different setup. And that's what the Z-transform gives us. It gives us an extension of the transform domain ideas to signals that don't have Fourier stuff going on. So again, what I'm going to do is I'm just going to try to plug this into the series and see what all happens. So let's plug it in. And what happens? X of z equals the sum over all n of x of n, z to the minus n. And if I plug in x of n equals z0 to the n u of n and chop the sum off at n equals 0, as the u of n does, I get this z over z0 to the minus n. Now, we've seen that guy before today. That's like a geometric series. In fact, it is a geometric series. And so what this does, it converges only when this thing is bigger than 1 in magnitude. Let's put it this way. It converges when magnitude of z over z0 is bigger than 1, and it diverges when magnitude of z over z0 is less than 1. And these two things together imply that R sub A is equal to mag z0. And when z satisfies z bigger than mag z0 in magnitude, our old friend formula for the geometric series tells us, so when z is bigger in magnitude than z0, geometric series implies that x of z equals 1 over 1 minus z0 over z, because the gamma here, the gamma to the n is z0 over z, and that's z over z minus z0. This is the way I prefer to write it. A lot of people prefer to write all z transforms in terms of powers of z inverse. I kind of loathe that, and if I see you doing it on a test, I won't take anything off, but it just strikes me as super ugly, and I don't know. I could go on and on. But anyway, bottom line is this. The signal x, whose specification is z0 to the n u of n, has z transform with the formula part, z over z minus z0, and the ROC part, magnitude of z0 less than magnitude of z less infinity. So this is our R sub A, and here R sub B is infinity. Now notice that whenever you have a signal that is 0 for time less than 0, the left series is trivial. So one feature of this example, note, when x of n is equal to 0 for all n less than 0, the quote-unquote left series converges trivially. For all z, that is to say, for any such signal, the r sub b thing, the outside of the region of convergence, is going to be infinity. And that's what we have in this example. Okay, any questions about this? Because if you understand this one and the next one, I think you'll pretty much understand everything. Come on, be brave, Nathan. I know you have a... No, you don't have a question. Actually, I'll pause between these two. Let's take the 3-minute break, and then we'll do the other one. Not sure. It may cost me students from my classes, whatever. We'll see. Yeah?
Touch real quickly on my theory about the different methodologies.
Yep.
Depending on your medium of viewing the photograph. Like, because I looked at it on my phone, so I was like zooming in on each face and going.
Right.
If you looked on your computer, you can like take it in all at once.
Yeah. So the medium could have been, so if you, so did you do the first one? Did you do the, oh yes, yes, one, or no, 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 one? So you did the no, not him, not him, not him, yes, maybe, or, okay. All right, cool.
I don't know, when I looked at the picture, I just sort of looked at it, and I immediately narrowed it down to 2 options.
Okay.
And then after that, I just looked a little more carefully between those two, and I was like, okay, it's definitely.
Okay, yeah, because that's, somebody else sent me an email and said, it took me 7 seconds. That's what he said, so. I think, I didn't say which one was me. I asked you to pick it out. And I'm not telling you which one is me. Everyone who's guessed so far has guessed correctly, though, so you have a chance to guess it correctly if you want.
I looked at it and I'm pretty sure that I've read it.
Send an email, right?
All right. Okay, so let's do the second example, now that I've distracted you from. So this is example 3. X has specification x of n equals minus z0. So again, z0 is just going to be some given complex number, u of minus n minus 1. And if you want that written out in case form, this is what it looks like. It's 0 when n is non-negative, and it's minus z0 to the n when n is negative. Okay? So that's the second example, or the third example we're going to consider. Let's try to plug it in to the series for x of z, see what happens. So plug in, plug and play, let's say. X of z is the sum over all z of x of n z to the minus n. And that's the same as the sum from n equals minus infinity to minus 1 of minus z0 to the n z to the minus n, which is z0 over z, or, yeah, z over z0 to the minus n. And if I change indices of summation here, let m equal minus n, this is the same as the sum with a minus sign from m equals 1 to infinity of z0 over z to the m. Okay, so now we've got it in geometric series form. You can see when it converges. It converges when the magnitude of z is less than the this isn't, I did something wrong here. Let's figure this out. Oh, this stays z over z0. Yeah, that's right. This converges when the magnitude of z is less than the magnitude of z0 because it makes the gamma thing, the thing that's raised to the m, less than 1 in magnitude. So this converges. I'm going to try to do it as much in parallel as the other example as I can. Converges when magnitude of z is less than magnitude of z0. It diverges when magnitude of z is bigger than magnitude of z0. Together these imply that r sub b is equal to magnitude of z0. And it's not quite a geometric series. It's a geometric series missing its first term, right? It's m equals 0 term. So this comes out to be negative, parentheses, 1 over 1 minus z over z0 minus 1. That 1 represents the m equals 0 term that's missing from that series. And lo and behold, what does this come out to be? It comes out to be z over z minus z0. And that looks awfully familiar because that's the same formula we got for the previous example. Bottom line, oh, by the way, you and Balaj, Manish, you were the first ones to guess, to send an email. But that's probably because you were just nerdily watching your email constantly, like I do.
I have it open in a separate tab, and I'm doing work on the other tab.
Oh, okay. Yeah, I'm sitting there at home. I have the, you guys probably read your mail on your phones now. I have my laptop sitting there, actually to my left. And every time an email comes in, I see it right away. So anyway, the bottom line is that x of n with specification minus z0 to the n, u of minus n minus 1 goes with x of z equals z over z minus z0. And region of convergence is 0 less than magnitude of z less than z0. So r sub a here is 0, and r sub b is magnitude of z0. And again, we don't include z equals 0 in the ROC, even though the series does converge as z equals 0. Okay, so what's the moral of these last two stories? Same formula, different regions of convergence. So note, the x of z formula is the same in examples 2 and 3, but the ROC x is different. And that's why, or part of the reason, it's important to lug this ROC along as part of the specification of the Z-transform. Okay, so for example, let's put it in Ho Plaza terms. Someone comes up to you in Ho Plaza and says, I have this signal, but I don't have the signal, I only have its Z-transform. Its Z-transform is z over z minus 3. What's the signal? What would you say? Yeah, you don't know. You would just either, if you wanted to be really zen about it, you would just remain silent. But I would probably, to be helpful, I would say, well, what is the ROC? And if I wanted to be sort of rude, I would just say, I don't know, and see if, throw down the gauntlet and see if the person picks it up. Okay, bottom line, you need the ROC to specify the Z-transform. And that's why Peter Dorshuk doesn't like to see a Z-transform without a region of convergence at all. Okay, now it turns out that these examples are the three examples we've done so far, the delta function, and those two examples are like the the seeds of this huge tree full of prototype examples of Z transforms. So, turns out that you can use operational rules for the Z transform, a couple of which I'll go over in a second, to generate a whole ream of prototype examples that follow from these. So you can generate, and you can see the monograph to see how this is done, a whole list of prototype examples. That's what I like to call them. Of Z transforms. And they come in pairs, just like 2 and 3, the ones we just did. And here's one such pair. This is the general form of such a pair. If you have x of n equals, has specification n choose m, z0 to the n minus m, u of n, that signal is going to have Z transform formula x of z equals z over z minus z0 to the m plus 1. ROC, magnitude of z0 less than magnitude of z less infinity. And the signal with specification x of n equals minus n choose m. Everybody knows what I mean by n choose m, right? Yeah. z0 to the n minus m, u of minus n minus 1. That signal has same formula, but opposite region of convergence. And really, these prototype examples are the only ones you ever need for most of the applications you consider at this level. Okay, so anyway, before we move on to talk more generally about signals whose Z transforms are combinations of these, I want to go over a couple of operational rules for Z transforms and also talk a little bit about how we use Z transforms for LTI systems. Okay, so some operational rules. And actually, I won't say some, I'll say 2, because as usual, there are more operational rules than we ever really want to worry about. But there's 2 really important ones. And can anyone guess what they're going to be? Convolution rule is one of them. What's the other one? Time shift rule. Excellent. You've learned your lessons well. Okay. Time shift rule. Oh, wait. Before I do those, I want to talk about linearity, because that's a little bit subtle. Okay. The Z transform is linear in the following sense. Okay, now, before writing anything down, let's think about why it might be subtle to deal with linearity here. We want to be able to say something like, if x1 has Z transform capital X1, if x2 has Z transform capital X2, and I take a linear combo C1 x1 plus C2 x2, I get C1 capital X1 plus C2 capital X2. Right? We want to say something like that. But what is the sand in the gears? What's missing here? It's the same thing that's missing when the whole plaza person comes up and says, what is the Z transform Z over Z minus 3 will? Regions of convergence. So how do you take a linear combination of regions of convergence? Or, Okay, yeah, we need to worry about the regions of convergence, okay, is really what I'm going for here. And I want to see how this works. If x1 has Z-transform capital X1 with some associated ROC sub x1, and x2 is another signal that has Z-transform capital X2 with its own region of convergence, and and the intersection, so you had that right, and will also, ROC sub x1 intersect ROC sub x2 is non-empty, then for any constant C1 and C2, and I'm assuming they're all complex things, so constant C1, C2, and C, we have the following. That if you take the linear combo oh, that should be an ROC sub x2 right there. I'll fix that later. The signal x, C1x1 plus C2x2, is going to have Z-transform capital X equals C1 capital X1 plus C2 capital X2. And the ROC for X is going to contain that intersection. And usually it's equal to that intersection, but sometimes it's a proper containment. Give you an example of a proper containment in a moment. So that's what linearity is for the Z-transform. If you have two signals whose regions of convergence don't intersect, then there's going to be at least one linear combo of them that gives you a signal that doesn't even have a Z-transform. So for all intents and purposes, you can only linearly combine signals and expect to have a Z-transform arise for the linear combo when the ROCs for their Z-transforms intersect. Okay, so let's look at one example of proper containment. And I think this is in the monograph. If it's not, it should be, so I'll have to go back and write it in. How about if I take x1 equals a unit step? This is of the special form 1 to the n times u of n, right? So therefore, it has a Z-transform z over z minus 1 with ROC 1 less than magnitude of z less than infinity. Similarly, x2, and you can figure this out for yourselves, if you take shift sub 1 of u, that has Z-transform x of z equals 1 over z minus 1 for 1 less than z less than infinity. So this is ROC sub x1, and this is ROC sub x2. They're the same. But if I take x1 minus x2, what signal do I get? Yeah, a delta. And that has Z-transform x of z equals 1 with region of convergence 1 or 0 less than magnitude of z less than infinity. And that contains and is not equal to ROC x1 intersect ROC x2. So that's an example where region of convergence of a linear combo can exceed the intersection of the regions of convergence of the combinands in the linear combo. Yeah, Denzel.
What happens when the regions of convergence just have no intersection, but you still try to do a linear combination?
Okay, the question is, what happens when you have two signals with Z-transforms and the regions of convergence of those two things don't have any intersection and you try to do a linear combination of those two signals? Well, nothing happens when you just take a linear combination of the signals, but as soon as you try to compute a Z-transform, like the Earth goes into a black hole, essentially. You know, something like that happens. The sky falls. You know, you could end up wasting your whole day trying to find something that isn't there. That's, you know. When they opened the Large Hadron Accelerator in Europe, people were actually worried about the end of the world, right? True. People are always worried about the end of the world. But in this case, it might actually have happened. We don't know. We might be just on one branch in many parallel universes. And one of them, the world ended, right? So is that a good way to think of it or a bad way to think of it? Okay. So anyway, that's the linearity property. Now for the two operational rules. And these are pretty easy to prove. There's a little subtlety with one of them because of regions of convergence. Time shift rule. If you have a signal x that has Z-transform capital X with ROC sub x, then for any n0, the signal y equals shift n0 of x has Z-transform. First, I'm going to give you the formula, then I'm going to give you the region of convergence, which is what one has to do. Formula part is z to the minus n0 times the Z-transform formula for x. And the ROC part is going to be the same as the ROC for x. Very easy to prove that. Proof is in the monograph. You just plug in y to the formula for the Z-transform, and you observe that the series converges for exactly the same values that it converges when you plug x in it. And every term features as e to the minus n0, so you factor that out, and voila, you have that formula. Convolution rule. If you have two signals, say x1 and x2, with respective Z-transforms, capital X1, region convergence ROC sub x1, and that reminds me, I have to, did I lose my opportunity to fix that? No, it's the next board. X2 with Z-transform cap X2 along with ROC X2. And the regions of convergence intersect. Then, first off, the convolution of the two signals exists. So y equals x1 convolved with x2 exists. And thus you can tell just by looking at ROCs for Z-transforms that the convolution of something, of two signals exists. It turns out not to be quite equivalent, but almost. and has Z-transform, anybody care to hazard a guess what the formula for y of z is? Yeah, x1 of z, x2 of z, right. Convolution always turns into multiplication. And the ROC for y, again, as in the linearity property, is going to contain the non-empty intersection of the ROCs for x1 and x2. And usually it's equal, but not always. Okay? And that's also easy to prove. The monograph has a proof of that. Now you may ask, well, do you need, like if you have two Z-transformable signals whose regions of convergence don't intersect, is it possible that their convolution also exists? Turns out yes, but it's rare. Okay, and I give an example in the monograph. And in that case, that convolution doesn't have a Z-transform. So you need this condition for both the convolution to exist and have a Z-transform. Now, clearly, this convolution rule provides the key for how we apply the Z-transform to LTI systems. So, how does this come up? Z-transforms and LTI systems. Suppose you have a discrete time, linear time invariant system with impulse response h. We say that the system has a transfer function when h has a Z-transform. And just as not every system has a frequency response, not every system has a transfer function. But lots of them do. And in this case, that Z-transform is the system's transfer function. So remember, the Z-transform has a formula part and an ROC part. So saying the ROC is part of saying the transfer function. So the transfer function is the Z-transform of the impulse response when it exists. So if someone comes up here in Whole Plaza and says, hey, you know, I have this discrete time LTI system. Its transfer function is z squared over z squared plus 7z plus 12. I want to find the output of that system when I drive it with a unit step. What is it? What would you say? Sorry? Okay, you multiply, but then what do you do here? If they only told you that the transfer function was z squared, z divided by z squared plus 7z plus 12. What, Alec? We'll do that later on. We're going to do partial fractions by Zen. Some of you have seen that and some of you haven't. Okay, but you're missing the point of my question. If someone comes up to you in whole plaza and all they tell you about the system's transfer function is that it's z over z squared plus 7z plus 12, what haven't they told you? The ROC. It makes a difference. Depending on what the ROC is, and there are three possibilities for that particular example, the response of the system to a unit step will be different. We'll see that shortly. Transfer function isn't just a formula. It's a formula along with a region of convergence. Okay, now I'm going to correct this ROC2 to be ROCx2 because that's been bothering me for the last 17 minutes or so. Okay, so given this definition of transfer function, we can apply the convolution rule to see what happens when I put in a z-transformable signal x. And when I can tell right away by intersection between ROCx and ROCh that the signal has a convolution with h. But there's other things we can do with this definition of transfer functions. So actually, I'm trying to think of which order I want to do those in. So maybe we'll save that. Maybe we'll stop there. I know I owe you a minute from last time. So there you go. Okay.